welcome. As Peter said, I'm Oscar. The main author of this paper couldn't make it, but here I am to present it. We work at Block, and we are formerly known as Square here in the US. So the main topic of our paper is cryptographic subversion, right? So we will study how we can subvert a cryptographic implementation of a signature scheme, namely ECDSA. First, I wanted to give you a couple of examples of cryptographic subversion happening in real life. And the first one is this one that you are very likely to be very familiar with it. This is a pseudo-random number generator standardized by NIST and designed and backdoor by the NSA. I'm sure you have heard about this, ECDRBG. We are not going to get into the details here, but the high-level idea is that the backdoor designer has privileged access to this algorithm, and in particular, it can recover parts or the whole key stream of this PRNG, thus violating all the security properties that this cryptographic implementation is supposed to provide you, right? So that's one example of something that was in the news like some years ago. It doesn't need to be at the algorithm level. It can be like at a company level. For example, this is another example of Crypto AG, right? So like a Swiss company that sold you could buy like encryption equipment, and it turned out to be fully owned by intelligence agencies, right? And it was, of course, fully backdoor everything that was sold there, right? So the backdoor designers had privileged access and could basically decrypt communications protected by these machines. This is very fun, by the way. If you're not familiar with this, there's plenty of articles in the Wall Street journals, and there's a lot of information there. Cool. So let's go back to our paper. We study how to backdoor a signature scheme, and we are going to get a little bit more into details of what that means, right? So the main idea is that the backdoor designer modifies designer algorithm, right, or implementation, so that the designer unknowingly leaks the private key to the backdoor designer. How? Well, like the backdoor algorithm embeds the private key into the digital signatures, into the output, right? So we will see this into more detail, but you can see that this is very useful if the end goal is to forge signatures, right? If the end goal is for the backdoor designer to be able to produce signatures for any message that they want. In the case, for example, of cryptocurrencies, if this signature algorithm was to be used in a larger cryptocurrency protocol, that would mean that the backdoor designer could steal funds from the people that have designers, the wallets. Cool. So this is a high-level representation, right, of digital signature scheme protocol. So we have, on the left side, we have some kind of hardware that emits signatures, that generates signatures. So that's typically like an HSM or a hardware wallet or any kind of dongle that has some access to a private key and generates ECDSA signatures, right? Those signatures are typically public, right? Those are publicly verifiable. And that allows some recipients, some receivers, to transfer trust from the public key that they trust into a message that is signed with the corresponding private key, right? So that's what a signature scheme does. So far, so good, right? So in our setting, we assume, right, that the adversary controls the firmware of the hardware wallet, of the HSM, of the hardware security module where the signing implementation is happening. That's by assumption, and that's a quite strong assumption, right? We will see later that we need to protect that if we want to not be vulnerable against this class of attacks. Right, so by assumption, the attacker has some kind of access to the code that the designer runs. And the end goal of the backdoor designer is to leak the private key into the digital signatures itself. Because in a later step, the adversary will be able to inspect those signatures, right? Like to read those signatures because they are normally public, and then recover secrets, and then ultimately forged signatures, right? Again, if we were to implement this kind of backdoor in, for example, a Bitcoin hardware wallet, this means that the adversary can just steal funds from the seed, from the secrets that they recover from the signatures in a backdoor signature scheme. Okay. So I want to spend some time here reasoning what would be like a good backdoor, what would that look like, and which properties are we looking for, right? So what are the requirements if we were to design such an ECDSA backdoor? First one, ideally we want the backdoor to be as stealthy as possible, right? This means that it's hard to distinguish this backdoor just from the input-output behavior, right? So typically, you have some kind of Oracle level access to this signer, right? So you can see inputs and outputs. Inputs, in this case, are messages to be signed, and outputs, in this case, are signatures, right? So just by looking at that, it shouldn't be feasible for anybody to tell those backdoor signatures apart from non-backdoor ones, right? You want this to be stealthy. You want to fly under the radar as much as you can, right? It also means that the backdoor signatures, they just work. They're just normal, regular ECDSA signatures, like that normal, let's say, like a regular stock ECDSA verifier will pass signatures that are correct and will reject signatures that are invalid. So you still preserve the normal behavior of a signature scheme. You also want the algorithm to be efficient, right? You don't want to have the backdoor signer to take an enormous amount of time, because otherwise, you can see that there is something fishy going on probably. So that's also another requirement, ideally, that we want. Ideally, we also want to leak as many bits as possible per signature, right? So there is a lot of prior work on this, mainly from Simmons in the 70s. And they typically leak a few bits per signature, right? That's very good, right? But ideally, you want to leak as many as you can. Typically, you don't need to leak like thousands of bits. Typically, you just want to leak maybe like 256 bits, right? Which is, for example, the size of a BIP32 seed, right? Of a seed of your protocol, of a secret seed of your protocol. So you want to leak 256 bits in as few signatures as possible, right? Also, you want this backdoor to be easy, right, and robust to deploy. What we mean by this? So it's very easy. Like these protocols in which you cannot assume that the receiver is going to get the signatures in the same order as they were generated, because maybe there is some reordering happening, or there's some signatures that are just missing. You want this scheme to be robust against those kind of things that can happen. Also, you want the backdoor to be, you want to be able to implement this backdoor after, let's say, your hardware security module has been deployed in the field, right? So you want to be able to ship this backdoor as a firmware update, right? And that typically means that you want to ship this backdoor after key generation has happened, right? One very common way to backdoor and one very easy way to backdoor, such as signature scheme, if you were not to take this requirement, would be just to backdoor the key generation process, right? That's an obvious way, but you want to ship this backdoor as a firmware update, or at least have the possibility of doing so, right? So that excludes backdoors on the key generation process. Also, you want to not need persistent storage, right? So typically, those signers, those hardware security elements that perform the ECDSA signatures are very limited devices where persistent storage is very expensive, or maybe scarce, or maybe non-existent, right? So you don't want to rely on that. You don't want to rely on flash or something similar to store something that your backdoor may need. So you don't want that, right? Okay. So those were like nice to have, and actually those are properties that we satisfy with our construction. I'm not going to get into a lot of the details of our construction. I'm just going to give broad strokes. But if you have any questions, I'm happy to take them. The basic idea is to use Simon's early work, right, in which you are cooking ECDSA nonces, right? I mean, as you remember, in ECDSA, you typically have, not always, but you typically need to generate a random nonce, or normally people also call it like ephemeral key, or or secret nonce. And you have to be very careful, extremely careful generating those. And you have some leeway there, like as Simon said, as Simon showed, you have some leeway to how to pick those nonces in which you can encode a subliminal message into some part of the signature. So we are leveraging that. We're reusing that. There's two things that we try to improve here, right? One is leaking like maybe 256 bits, so leaking way more bits, so that you can leak your whole seed, not only like 40 something bits. And you want to deal with this thing that we mentioned before, which is like missing or reordered signatures. There's two parts of this construction. The first one is chopping your seed into smaller chunks. So this is one, if you want to see it as a coding problem, this is a very simple coding problem. So we are not leaking like a specific chunk of the seed, let's say bit number 0 to 10. We are not doing that. That would be one way, but that wouldn't be resistant to reorderings or missing parts. Instead of that, we are leaking a linear combination of the seed bits, right? And which linear combination we are leaking? Well, that's indexed by some public information, which is the message, So that's what we try to represent there. You start with a big seed, let's say 256 bits, and you are going to leak only a linear combination, let's say a linear combination resulting in 20 bits, let's say, and via matrix multiplication, and which bits you are picking, which bits you are picking to XOR together. That's determined by some public information, which is the message, right? I mean, actually, it's a little bit more complicated. It's not only the message, but essentially, it is the message. And at the end, you end up with a small chunk, let's say, of 20 bits that you are leaking via Simon's subliminal ECDSA scheme. And you have to repeat this, right, over several messages. So you will be picking several linear combinations of the seed bits, right, until you have enough equations to solve with your favorite your favorite Gaussian or whatever, however you solve linear equations over GF2. That's basically it. The second part is, as I mentioned, recovering or leaking like 20 to 40 bits per signature, right, as Simon's showed. We do that by solving reduce the generate instance of elliptic curve discrete logarithm problem, because it's over an interval. You know that the scalar, the secret scalar that you are trying to recover, is restricted to a small-ish interval in which you can just brute force if you have enough memory, or you can do trade-offs. You can have time memory trade-offs. You can have tables to do baby big step like algorithms like this, or you can just, for example, use Pollard's lambda. That's very efficient memory-wise, and also gives you a nice quadratic speedup. So that's actually pretty nice and suitable for this application. It's basically ECDLP over a short interval. You have to repeat that for quite some signatures, and then you just feed it to your linear equation solver and recover the seed. That's basically the construction. So we can go to demo time. But before, as everything good in life, we have to go to the commercials. So we are hiring. If you like this stuff and you want to write some code, I will be super happy to talk to you. That's my email. I'm hiring for security engineering positions. So we do applied cryptography, write code in different languages and different systems. So yeah, just drop me an email and say hi, and we can take it from there. Cool, as promised, this is the demo. This is basically a short, end-to-end implementation of what we described. We are leaking a few bits per signature. It says 19 bits per signature. Okay, and after a while, you have enough signatures. You can solve the linear equation, and then the seed pops up. We actually also implemented this into Bitcoin testnet, so that you can recover those signatures from another place, from a publicly available source, and just execute this attack. Cool. That's what I mentioned. So we implemented this in testnet. We need some computational resources, but nothing extraordinary, nothing beyond a cool laptop. And we also learn quite a lot of things, which is actually the motivation of this research, on how to design this properly and which parts need to be hardened to prevent this class of attacks, right? So we have a lifetime responsibility to keep the firmware signing key safe. And not only that signing key is important, but there's lots of places in which you could inject this backdoor. In your CI/CD pipeline, in your build system, you can steal the firmware keys, you can hijack the flashing process of your hardware. There's lots of places that you could plant this backdoor, that you could ship this backdoor. And also, we have some mitigations in the paper that we can talk about if you're interested. Basically, split trust, right? You basically want to divide and not put all the eggs in the same basket, right? By using, for example, multi-signature schemes, or maybe MPC, if you do it really right, it could help in this kind of stuff. Also, there is work on firewall signatures that is very useful in this kind of applications for mitigating these kind of things. Also in the same vein of splitting trust. That's it. Thank you for listening, and happy to take any questions.